at 5% interest. How long does it take to double? Well, in the previous example, we learned that the first thing we always have to do is find the growth rate k. How do we find it in this case? Well, in this case, it's given to us. 5% interest, that's the growth rate. Your bank grows by exactly what the interest rate is, so I already know that k is 5%. 5% means 0.05. And this means the size of my bank account at any time t is just the initial value, which we decided was $1,000, times e to the 0.05 times t. I want it to double, so I want to figure out which time it will be equal to what? Well, it's $2,000. When it will equal $2,000? 2,000 is 1,000 times e to the 0.05t. If I divide, I get 2 is e to the 0.05t. Now take the natural log of both sides. The natural log of 2 is 0.05t. Did you catch that step? Remember, natural logs get rid of e, so log of e to the 0.05t is just 0.05t. And that means finally that I can solve for t. T is 0.05 over the natural log of 2, which is a little bit less than 14 years. It's about 13.86 years. You have a bank account that pays you 5%. If you invest in a stock that grows at 5% a year, however much you invest will double in 13.86 years. And over the next 13.8 years, it will double again. Over the next 13 years, it will double again. It doesn't go by the same amount each time, it doubles each time, and you can imagine how powerful this is. In fact, I think it was Albert Einstein who said that compound interest is the most powerful force in the universe. Those of you who are still in high school and watching this lecture, take note. Start saving for retirement now. Alright, let's move on. In fact, this doubling time was sort of nice. We got this for 5%. What if you had made a different amount in your retirement account? This 0.05 was our value of k. That we followed that value of k all the way down to here and nothing really happened to it. And so it shouldn't surprise us if we can say this much more generally. In general, let's say something growing exponentially you have anything, bank accounts or bacterial colonies, at rate k will double in natural log 2 divided by k years. Or hours, or days, or whatever it is we're measuring this in. If it goes up by k per unit time, 5% a year, 5% an hour, we'll double in natural log 2 over k years. And I would point out to you that this is a nice party trick. The natural log of 2 is 0.693. It's very close to 70. It's hard to do math with natural log of 2 in your head, but it's not hard to do math with 70 in your head. So imagine this as a 0.70. Imagine this as a 70. 70% is 0.70, and imagine this as a percent. What if you make 7% a year? How long will it take to double? Well, 70% divided by 7% is 10, right? 10 years. If you invest in stocks that grow at 10% a year, how long will it take to double? Only 7 years. This is a great trick. It's very nice to be able to do this in your heads. But also note, you can use this trick at parties. If you're sitting around with a lot of people and someone says, I'm making 14% a year on my stocks. I wonder how long it will take my money to double. All you have to do in your head is think, what's 70 divided by 14? 5. 5 years you can spout out and think how cool you will look. Don't say that mathematics class never taught you something useful. Doubling time formulas. Use them wisely. Use them now. There's one more side to this, however. It is true that exponential growth is very common. It is true a lot of things grow at a rate proportional to their current value. But the flip side of this is shrinking. Some things shrink, they decrease, they decay at a rate equal to or proportional to their current values. In cases like this, we don't look at exponential growth, we look at exponential decay. The most popular, the most famous, the best useful example of this is half-life of various atomic nuclear substances. Everything from plutonium and uranium to medical compounds to carbon decay this way. The way we date old trees, for example, is carbon dating. Carbon-14 turns into carbon-12 at a nice systematic rate. Uranium-236 turns into uranium-234, I think it is, at a certain rate, and this is exponential decay. It turns out the math is exactly the same. All that happens when you're working through the problems, the K that you find ends up being negative. Beyond this, there's no difference at all. And in fact, let's try this. So, iodine 131 is a useful medical compound because it has a half-life of 8 days. What does this mean? Well, if you say start with 32 grams of iodine 131, then after 8 days, half of it will be gone. After 8 days, you'll have only half. You'll have 16 grams. After 16 days, this is the part that seems a little bit funny. If you lost 16 grams in the first block of 8 days, shouldn't you lose 16 grams again in the second block of 8 days? No, you only lose half. Only half every time. So after 16 days, you'll have 8 grams. And after another 8 days, when we're up to 24 days, we're down to 4 grams. Every time 8 days go by, the total amount of iodine gets cut in half. You can imagine this being useful if you want to track, say, the motion of blood inside a patient over days. You put some of this iodine into them, you watch where it goes, and you can measure using various devices how much there is later. Half-life, the amount of time it takes for half of something to go away. By the way, if you find this puzzling, if it seems weird that in the first 8 days you lose 16 grams, but in the second 8 days you lose much less, if that bothers you in some way, then run out of class as soon as it's over and find your closest chemistry teacher to talk to them. It's a really interesting story, not one we have much time to go into here, but think about this. It's kind of strange. It's almost like when the iodine is disappearing, when it's decaying, when it's going away. It's almost as if it knows how much more iodine there is around it. So it knows that only half of it should go away. Of course it doesn't know what's around it. Of course there's a good reason, and I will leave that reason for you to find out. Let's take these half-lives and try to turn them into a problem. Let's first find the growth rate, or in this case the decay rate. Let's find K for iodine, in particular for iodine 131. Well, if we started with 32 grams, I told you we're going to use the same equation. N of T equals N0 times e to the kt. I could start with 32 grams. I already know half will be gone after 8 days. So I know what N of 8 is. I know that's going to be my initial amount, 32, times e to the k times 8. And I know after 8 days only half is left. So I know 16 is equal to 32 times e to the k times 8. If I divide, I'll get 1/2 equals e to the k times 8. And now I want to solve for k, so what do? If you said take the natural log, you're absolutely right. The natural log of both sides would be the natural log of 1/2 equals k times 8, and then all we have to do is divide by 8. K is the natural log of 1/2 over 8. It's about equal to negative 0.086. The decay rate. And every block of time, in this case every day, I guess is what we're measuring in, we lose about 8% of what we had. Now that we know K, and let's remember this number, negative 0.0866, we can use it to find other things. How about this, that the hospital starts with, let's say, if the hospital starts with 10 grams of iodine 131, how much will be left in 30 days? This is an important question for the person in charge of supply at the hospital. You see, iodine decays, that's the whole point, right? So if you buy it and put it in the closet and come back after a week, it's not all there. How much more will you have? This is something we might very much want to know. How much will we have left? I would tell you before we do this, if you want from Liberty to think about these problems, you can almost solve these in your head. Every time 8 days go by, it's cut in half, right? So after 8 days, we're down to 5 grams. After 16 days, we're down to 2.5 grams. After 24 days, we're down to 1.25, 1.25 grams. And then we have only part of a decay left. So so we probably guess a bit less than a gram. Getting more precise in our heads is maybe difficult, but getting close to that isn't too difficult. A bit less than a gram we should probably think about. And if we stop and think about that first, it'll be a useful check on our work. If we screw it up, as we know, we are all too wont to do sometimes. Let's try this now that we know what k is. I know my equation is always, and I'm going to keep writing this just so we remember, this is the equation that solves all of these problems. I now know k, I know the time I'm interested, which is 30. I know my initial value, 10 grams. What I want to find is how much there will be left. So n of 30, the thing I'm trying to find, is equal to 10 times e to the negative 0.0866, I believe, was our number, times 30. I could simplify this first, but it's not too hard to punch this directly into the calculator. In fact, can we do this? This is not showing up very well. You can trust that I'm doing this on the side. 10 times e to the 0.0866, that should have been 6, times 30 gives us a number which is about equal to 0.744 grams. Remember in our heads we say it was a bit less than 1 gram, and we got 0.744? It's not too difficult to see this. We simply plug into the equation and know exactly how much there will be left. The answer is not that much. If we start with 10 grams, after a month there will be less than 1 gram left. When the hospital buys it, they would best use it quickly. Let's ask one more question about this iodine before we're done. If we start with 10 grams, as we did before, when will we have a milligram left? When 0.001 grams left. Maybe this is the smallest amount we can detect with easy techniques in the hospital. I don't know if that's true. Maybe it is. How long will it be until we have only 0.001 grams left? Is this easy to solve? Yes, it is. It certainly is. Let's start with the same equation we always start with. N of t equals n0 times e to the kt. I now know what the amount is. Remember, this thing on the left is the amount at time t, and I know what that amount is in this case. I want to find the t when this is 0.001. I know the initial amount is 10. I know what e is. I know that k is still 0.0866, and the only thing I want to find is t. So we solve this for t. If I divide both sides by 10, I have 0.0001 is equal to e times e to the power of negative 0.0866t. How do we get rid of the e? If you said take the natural log of both sides, you're absolutely correct. Take a natural log of both sides, and we get, I'm going to go ahead and be sort of a bad mathematician here. It's best to leave the natural log there until the very end, but I'm going to look for a decimal in the end. I know that already. Let's just take the natural log of both sides now. This is negative 0.921 is about equal to negative 0.0866t, and it looks like all I have to do now is divide both sides by 0.0866, which means that t is about equal to 106.35 days. If you buy 10 grams of this stuff after only about 3.5 months, we'll have only a milligram left. To summarize, if we have any population, any amount, any value which is changing at a rate proportional to its current value, population that's growing, a compound that's decaying, a bank account that's slowly increasing, we can always solve problems like this with exactly the same equation, with the exponential growth and decay equation. We have time, we have the initial value, we have the amount that we're looking for. Using the equation in a variety of ways will always give us the answer, and this is yet another reason to be grateful for the value e for the exponential function.